All right. Well, welcome to the Utah Kubernetes meetup. Good to have everyone here. And again, grateful to have Phil, who's our presenter. And he lives in an amazing place, so I'm not even worried about having him take this time out of his wonderful schedule of being in New Hampshire in a beautiful place. But we do appreciate you presenting tonight. I'll let you introduce yourself. And as I mentioned before, we are recording this. And also, I talked to Phil earlier. Questions are definitely invited during the presentation. As always, munch quietly because these microphones are really, really good. And if you have things that you have during the discussion that you want erased out of it, let me know and I can edit it out. But I've done that a couple of times. Anyways, welcome. And again, speak as long as you'd like, and then Q&A afterwards as well. And I'll just hand it back over to you, Phil. Thank you again.
Sounds good. And whoever was talking about DevOps days in Salt Lake, somebody should exchange information with Jeremy in the audience. We participated in the Austin DevOps days, so it might be something that we would be able to participate with from a sponsorship perspective. So hi everyone. Phil Andrews, field CTO at cast.ai. I've been here coming up on 3 years. I basically live and breathe Kubernetes optimization for the past 3 years. We've worked on a lot of different projects, small companies, a couple hundred cores worth of Kubernetes, large companies, a couple 100,000. The largest cluster we interacted with was, I think, 264,000 CPU in a single cluster on GCP. So some pretty big infrastructure that we worked with. So today I wanted to kind of share some of the stuff that we go through when we are working with, different environments, some of the pitfalls that we've seen, and kind of go through the optimization there. Past life, I was director of engineering at Oracle Cloud. So I am an actual engineer. I'm not a sales guy. Sorry, Jeremy. I do my best. But we'll go from there. Also, I apologize in advance for how terrible my slide deck may be. I never use slide decks. I always just show people around the actual product when I'm working on things. So bear with me on slide deckage. All right, so go ahead and kick off. If I can get my slides to, there we go. So some of the data I'm going to reference in here is some data that we collected last year. We had about 4,000 clusters that we were connected and got insights from. That was from tiny little clusters of 10, 20 CPU all the way up to, like I said, a couple 100,000 CPU in a single cluster was our current record. So we got a lot of information out of that data, and we've done it for 2 years in a row now. So we've kind of started getting some trending data. So I'm going to touch on some of that data, and then I'm going to touch on how we can actually fix some of those issues. So we'll go from there. This is what I talked about. So this was from the 2023 calendar year. This is across AWS, Azure, and GCP. So we have pretty good visibility across all three of them. Obviously, the bulk of our data is on AWS, about 50%. We get about 30% on GCP and about 20% on Azure from the different cloud spreads. 13%. This is a horrifying number. Absolutely horrifying. 13% of the actual compute capacity in Kubernetes across the board is what's actually consumed by applications. There's no other area of a business that people would tolerate a 13% utilization rate, right? This is abysmal. But it just goes to show that Kubernetes is hard, right? It's still better than VMs. It's better than what we had, but it's still hard to get good efficiency on it. There's a tremendous amount of waste in compute overall in Kubernetes, 13%. And this data is backed up. AWS did a study a few years ago. I think they came out with like 13.2 or 13.8%, somewhere in that neighborhood. I think GCP did one 5 or 6 years ago, and it was on VMs, it was on GCE instances, and they were in the 11 or 12% range. It's pretty consistent, and it has been pretty consistent over the past few years, that in that 13% range is how many CPU cycles are actually consumed of cloud compute. It's awful, because that other 87% is literally burned money. It's money that is absolutely wasted. And the goal of Kubernetes was to use the boxes better, right? Package applications, get better quality of service, be able to identify, how we can align containers and workloads and applications better so that they could use more of the resources and get better packaged. But in reality, that hasn't really happened to a great degree. It's helped in a lot of areas. It's helped with resiliency. It's helped with microservices. It's helped with a lot of other things. But utilization has not really gone up very much.
A question, Phil.
Go ahead.
In that stat, because we have a lot of AI stuff that's happening today, does that include GPU as well?
That doesn't include GPU. So we don't have stats on GPU utilization yet. We probably will in our 2024 report, actually, because we're starting to collect GPU utilization metrics this year. So hopefully next year we will have GPU metrics. Today we're mostly focused on CPU and memory. We do provision GPUs, but we don't capture utilization metrics yet.
Thank you.
Yep. Memory is slightly better, about 20%. Memory is also a lot more static. It doesn't bounce around nearly as much as CPU does, but it's also non-compressible. Right. So you have to give your resources the right amount of memory. But even within that, 20% is still pretty garbage, right? If you had a building that was only 20% used and 80% empty, it would be a very poor use of the building, right? If any real estate manager had that, it would be a bankrupt portfolio. So 20%, while better, still not great. There's a lot we can do to gain there. Memory is a little bit easier for the most part. Because it's relatively static, applications don't tend to bounce around as much on memory. They do a bit if they're ingesting off of a queue, and I can touch on some stuff around that. I don't have it specifically in the slide deck, but there are some ways to do optimization on queuing. But generally, memory tends to be a lot more static, especially where there's still a tremendous number of Java services out there where the heap is the allocation, and that's what this is looking at as well. If the heap size is 2 gigs, it's going to look like 2 gigs in Kubernetes because the heap appears as used. Golang, Python, other services are more realistic in their actual usage. So 20% is what we saw on the memory side of things. The gap between requested and provisioned is actually growing over time. So people are requesting more and still not using very much. It's slightly better from 2022 to 2023. The actual use percentage went up slightly. I think we went from like 12.2-ish to 13, but the requested went up even higher. So the delta between those is growing. So what you're paying for versus what you're actually using is even worse. So these are the 3 things that really drive a lot of issues and waste in Kubernetes. Over provisioning. Everybody's panicked that their workloads will not have enough capacity. And so therefore there's multiple levels of waste. They add waste into the requests and limits because they're worried that they're not going to have enough, right? Most people don't performance test extremely well. So you kind of over provision there just to make sure you don't get woken up at 2 a.m. because something died. There's a lot of waste there. That's one section of the over provisioning. Right, and that one's really hard to capture. The next one is actually node usage, right? A lot of people are over provisioning the nodes that they're provisioning on, and I'll kind of go into why that happens. But there's 2 different layers of waste there: the actual physical nodes and the logical requests and limits on the workloads. When you stack those 2 together, we've seen clusters that were 95% over provisioned. I've seen a cluster go from $25,000 a month to $1,500 a month when it was properly optimized. Amazing amounts of savings and reduction with no loss in performance. None. In fact, the applications were typically running better because they were building them in a more resilient fashion, which brings me to my next one. Poor resiliency configurations, right? There are a lot of configurations out there in Kubernetes. Kubernetes is literally infinitely configurable. And I have encountered many of those infinite configurations over the past few years. A lot of them are bad. There are a handful that are good. There's some good best practices out there. Most people, and I apologize if this is anybody, wanted to get into Kubernetes a couple, 2 or 3 years ago. At the time, you Google how to use Kubernetes, you probably grab deployment off the internet as a sample file, do a little bit of modification for it. And that became the deployment file for an entire organization. Right. And then everybody copy pasted the entire deployment file and just edited maybe the image and a few environment variables. And so now you've got, a company that might have 250 microservices that are all built off the same root deployment file that nobody ever changed the requests and limits on. And I have seen very similar cases to that. Now you've got production with 250 workloads running. Some of them need 50 millicore, other ones need 500 millicore, and they're all getting, say, half a core. Not a great use of configuration. So we'll dig into that. And the other one is pricing arbitrage, right? And this one's a bit more dynamic. This changes cloud by cloud, but using spot instances effectively, right? There's still a lot of organizations out there that are not using spot instances. Sometimes it doesn't make sense. I've talked to a few organizations that have such ridiculous discounting with their cloud contracts that spot instances can actually be more expensive than on demand. But that is extremely rare. Most organizations that are under $20 million a year spend in the cloud, spot is still going to be advantageous, and it's not going to be contractually binding. So there's a lot of good use cases out there for spot instances. If you don't trust them in prod, there's still a lot of good use cases in the lower environments. So I'm going to kind of deep dive on each of these 3 points kind of as we go through. Any questions, comments on what I've touched on so far? No? We're good? All right. So automation is kind of a big part of this, right? And obviously, automation is very important, whether it's, cast.ai or whether it's some other company out there or whether it's open source tools. Automation is the key to solving a lot of these problems. And we'll kind of go into how that is. You can select different sizes, types of compute, selecting the right requests and limits on your workloads, binpacking, all of those things are infinitely easier with automation. You cannot do this alone. And again, whether it's an open source tool that's helping with this, there are plenty out there. A lot of people are using open source HPA, using Kata, the automation, right? Kata is a fantastic autoscaler. We use it internally. I'm going to pitch for Kata right now. It's great for queue-based workloads. Anything like that is going to help set you in the right direction. The worst thing you can do is just have a statically defined cluster that doesn't auto-scale in any direction and has no automation in it. Those are the biggest savings that we typically hit when we were interacting with customers, is when it was set up and nobody ever automated it. It's got static settings, they've got a static number of replicas, they've got a static number of nodes, and they over provision it because they have to provision for peak capacity because they're not using automation. It's the same problem Amazon had when they created AWS. They had to provision for Black Friday traffic year round. And so they sold the rest of the capacity off the rest of the year. Well, you can't sell the rest of your capacity. You can't really do that. Your goal is to have just-in-time capacity. You want to only buy the capacity you need when you need it, not buy it year-round for the one time that you might need it. And that's what really catches up a lot of people that are working in Kubernetes, a lot of engineers. That and the poor bastards in DevOps actually get pulled in two directions, right? The developers want peak capacity all the time because they never want to have to worry about their workload going down. FinOps guys want there to be minimal capacity all the time, and the DevOps guys are kind of caught in the middle, getting pulled in two directions. So I strongly encourage for the DevOps folks that might be here today, stand up for yourselves. Strong DevOps teams lead to better organizations and better Kubernetes by far. The best Kubernetes infrastructures that I have seen are when the DevOps team had supportive leadership and they put their foot down and they would not allow people to put garbage workloads out into their infrastructure. They just wouldn't allow it. They said, no, unless you meet our standards, it's not going live. And if you have your CTO or your CIO's approval and they have your back because it's the right thing to do for the business, the development teams will fix it and they will do it right. So strongly encourage that. Some of you might already be too far down that path and it's hard to fix it once the horse is out of the stable, but do what you can. So the vast over provisioning. So this is kind of what I touched on before. Node over provisioning, poorly fit nodes. Most of the nodes that are provisioned out there today, somebody picked a node type 2 or 3 years ago when they initially transitioned to Kubernetes. Maybe it was an M5 2XL, M5 4XL, something along those lines. They built out their templates, they built out their node groups, and now they have 60 M5 4XLs as their cluster. And that's their whole cluster. Well, the problem is if you've got Java workloads and Golang workloads and Python workloads, and you've got batch jobs that spin up and down, and you've got Spark running out there, and maybe, for some awful reason, you've got, some stateful stuff running there. Those nodes are not going to be the right fit for all those workloads. And a lot of people think, I need to have a whole bunch of different node groups to fix that. I'm going to split my Java workloads into memory-heavy node groups. I'm going to split my Golang workloads into compute-heavy node groups. Node groups are sort of an antiquated mentality. Node groups don't actually have a place anymore. They existed at one point in time to segregate workloads, but Kubernetes has all the built-in configuration needed to do all of that without using node groups. The only reason node groups need to still exist right now is because people have been using them, and it would break too much infrastructure if you tore out node groups altogether. There's a few small edge cases where it does make sense to segregate workloads. One thing I advocate for is segregating stateful workloads away from stateless. I actually advocate for not putting stateful workloads in Kubernetes in the first place if you can avoid it. Using a managed service on your cloud provider is typically way better, but sometimes it comes with a price premium. It's an argument there. But if you at least put your stateful stuff in one segregated corner of your cluster, it's not going to contaminate your entire rest of your cluster. If you have 60 nodes worth of stateless work and 5 nodes worth of stateful stuff, stick those 5 stateful nodes in a corner, optimize them once, and just leave them alone. Focus your effort on those 60 nodes that you can actually help. Because you need to be bin packing. You need to be auto-scaling up and down throughout the day. You need to be selecting the right nodes for those workloads. You need to be able to move workloads around to get that 60 nodes efficient. If you've got those workloads that are on those 5 stateful nodes and they're spread across all of the other 60 nodes, it's going to make it so you can't bin pack effectively, right? Those stateful sets are going to lock the nodes where you can't downscale, you can't bin pack, and you're going to end up with a bunch of partially filled nodes that can't compress very well. The other one is the workload over provisioning that we talked about before. I can't tell you how many people we've talked to that have zero idea what their actual request to usage looks like. Maybe 1 out of 10 people that I talk to has a Grafana graph that actually tracks, usage versus requests. But in that case, it's usually alerting when the usage gets too close to the requests. They're not actually alerting in the other direction. So they're not alerting on underutilized resources. They're only alerting on overutilized resources. Again, they're panicked that they're going to use too much and get yelled at in the middle of the night. They're not worried about how little they use. But with proper HPA settings, with using, like I said, a tool like Kata or HPA with custom metrics, there's a lot of ways out there that you can horizontally scale that you can capture the capacity you need without having to over-provision things so severely. On the over-provisioning side of things. Oh, all right. Or resiliency config. This one's probably one of the hardest ones to solve because you have to know Kubernetes pretty darn well to be able to fix it. A big issue, pod anti-affinity. People love pod anti-affinity. Everybody thinks in that data center mentality. I can't have all my workloads on one box. If that box goes down, it's going to be terrible. I can't have all my workloads in one AZ. If that AZ goes down, it's going to be terrible. I can tell you right now, I've got one customer that runs their entire business in US West 1 AZA. AWS, literally the worst region you could operate in the world from a cost perspective. They run single AZ stacks in that one AZ, and they have never gone down, right? And that the reason for that is because they can't tolerate the cross AZ egress costs. They can't tolerate the cost of sending traffic cross AZ. So they're willing to accept the business risk of putting their entire stack in AZ. And in the 3 years that I've worked with them, they have never had a flooded in that AZ. They've never had a loss in that AZ. So the fear of losing an entire availability zone or losing an entire big chunk of your infrastructure is relatively overblown. That kind of dates back to the data center days when a stack could go offline because a PSU failed. Right? We've kind of moved beyond that. The cloud infrastructure out there today is extremely resilient. You might lose a node here and there. So you do want to have a resiliency across nodes, and you do want to have resiliency across AZs where you can. But it's not really, as long as your cluster is multi-AZ, if you lose an AZ, even if all your workloads were on that AZ, they're going to reschedule to the other AZs, and they're going to reschedule fast as long as you're using good best practices. So using something like topology spread across AZ, if you need to spread your workloads out across AZ, much better than pod anti-affinity. If you're using pod anti-affinity on something that horizontally scales, when you have 2 replicas, you only need 2 nodes. Great, that's easy. You stick it on 2 nodes that you already have. When you've got 50 replicas, now you need 50 nodes if you're using hostname topology. Most of your other work, that might be 50 new nodes. So now you're going to have one workload on, say, 40 additional nodes. You might have one on 10 nodes that are already in use, but then you've got 40 new nodes that have one workload running on them. That's extremely inefficient. Doing something like topology spread using Zone, you could spread those 50 workloads out and put, 15 in each, 16, 17, whatever it works out to be in each AZ, you're still going to have that spread. You're still going to have that resiliency. You're still going to have them spread out across boxes because they're going to naturally distribute across boxes when you have them distributed across AZs. Because one box is going to be full, and when you need a new pod, it's going to spin up a new box in the correct AZ. So again, using the automation, using the tools that Kubernetes gives you, you can spread those workloads out without hamstringing yourself using something like a pod anti-affinity. I've seen this happen a lot before. It creates a tremendous amount of waste in the cluster. The next point, pod disruption budgets, right? I would say probably only 25 to 30% of the customers I've worked with use pod disruption budgets en masse, right, across all of their workloads. Most customers have them on between 0 and a few workloads that they have out there. Pod disruption budgets are extremely important for making sure that your workloads can move around safely within the cluster. For those of you who don't know, pod disruption budgets are basically the number of your replicas that can be offline at any given time. So you can have min available, or you can have max unavailable, or you can have, I think you can do even available, no, max unavailable or min available. You can do percentages, or you can do static numbers. Percentages are okay if you have high replica counts. For instance, if you said, yeah, I could lose up to 50% of my replicas, but you only have 2 pods, now you can't move a single replica without violating that, right? If you say max unavailable is 20% and you've got 2 pods, you can't move a single replica because moving 1 pod would create a 50% unavailable, and it's going to violate your PDB, and now you've locked 2 nodes. Those 2 nodes cannot drain. Kubernetes will not allow them to drain because it will break the pod disruption budget. There's a little bit of wishy-washy space in the middle there. If it's close, Kubernetes will allow it if it rounds to certain areas, but generally speaking, bad pod disruption budgets are bad. Percentages are iffy. Don't use percentages on low count replicas because you'll end up locking nodes up, and then you create the same problems that we talked about earlier. You can't move things around. If you can't move things around, you're going to create waste because you have to be able to move things around to be resilient and efficient. So PDBs, either use static numbers, or if it's on a large replica, make sure your percentage makes sense for how many replicas you have and for the resilience that you need to work on. One really bad thing I see with PDBs is people copy pasta the same PDB across all 250 or so workloads that they have. And some of them only have 2 replicas and some of them have 50 replicas. Well, the same PDB doesn't work across all those. I know it's a pain in the butt to tune your whole deployment file, your PDBs, your settings for each individual workload, but it has to be done, right? It takes 5 minutes. It just needs to actually be done and focused on. It's tech debt. Most people don't like doing it, but it's super important. The reason pod disruption budgets are so important is because when you need to drain a node down, if you've got 10 replicas and a node has, say, 3 of them running on it, but you only have a max unavailable as 1, setting a PDB, if a tool goes out there, whether it's cluster autoscaler or something else, tries to drain that node down, it'll drain it. One of the pods will move. It'll get up and running on a new node. The second pod will move. It'll get up and running on a new node. The third pod will move. It'll get up and running on a new node. Now that node can be deleted and downscaled. So you've given the opportunity to be able to shuffle pods around and actually be able to increase resiliency and getting rid of waste there. PDB is super, super important and very poorly used by most people. Node groups, node pools. I think I touched on this a little bit earlier. I've seen one customer that we talked to that had 350 node groups in AWS. It was awful, absolutely awful. They were very, very poorly optimized because every single workload, every team, every workload, everything got its own node group because they were worried about tagging, and they wanted to be able to track costs using AWS tags and Cost Explorer. They wanted to make sure there was no, noisy neighbor issues. There was a whole bunch of excuses as to why they did it. But it created a tremendous amount of waste because every single one of those node groups is creating a bubble of unused capacity because you're trying to target a node size to a set number of workloads or workload size, and they never match perfectly. So now instead of having bubbles across, say, 3 node groups, you've got these little bubbles of waste across 350 node groups. It adds up a lot. Keeping your node groups and your node pools to an absolute minimum. And by absolute minimum, I mean like 1 or 2. I mean, maybe 3 if you've got GPU workloads and you want to put them in their own node group, like fine. 1 for GPUs, 1 for stateful, 1 for stateless. That's all you should need. People that argue I need a separate node group because I want to worry about noisy neighbor issues means that they have their requests and limits configured poorly. Or maybe they've got a high network throughput, but that's an edge case. I rarely see times where network throughput is so high that you need dedicated nodes. Most of the time, it's, again, for that fear of the unknown. It's that fear that something somewhere is going to cause me a problem and it's going to be a pain in the butt. And so that fear leads to waste. The last one is what I mentioned earlier, segregating stateful stuff from stateless. Very, very important. I've seen very large clusters that had Redis and MongoDB and all kinds of other stateless stuff, Kafka, spread throughout the entire cluster. We went to try to optimize and you couldn't move a single node. They were all 30 to 50% allocated. The request to on the nodes was 30 to 50%, and we couldn't do anything because we would have broken the stateful sets. So the first thing we did was, okay, look, let's go isolate these stateful sets. Let's move them to their own little corner of the world and tell them to leave everything else alone. If you can't get them out of your cluster altogether, just put them in a corner and tell them to mind their own business. Then you can focus on the stateless stuff. That you can actually help. Stateful stuff is never going to bin pack well. It's never going to be that efficient. Well, you can get it reasonably efficient, but it's never going to be great, right? Because it doesn't auto scale typically, and it's kind of not great for Kubernetes. But people love putting everything in Kubernetes. So isolate your stateful stuff. That's going to help a lot. Any questions? No? We're good? All right. The last one is spot instances, using effective spot instances. So whether this is using them in node groups, using a third-party tool out there, using some of the open source tools out there for scheduling, using spot instances effectively can save a ton of money. And I'll give a few examples here. The big thing here is being able to arbitrage, right? Keeping your mind open of what instances are out there, because you'll be able to save a lot more money that way. One example, right now in AWS, the G6 instance is the least expensive spot instance that I have seen in AWS in 2 years. They're running typically between 0.7 and 1.1 cents per CPU hour. That's normalized on CPU, ignore memory for the moment. They're effectively an M7i under the hood, but they also have an L4 NVIDIA graphics card on them. Super high performance, latest generation NVIDIA graphics card. Fantastic, wonderful, awesome, great, cool. Who cares? If they're on the spot marketplace, just use them as a regular compute instance. Nobody in their right mind would grab a G6 and schedule it as an on-demand instance to use it without the GPU. However, on the spot market, it is currently the cheapest instance you can buy, period. Why not use it? Same thing, I've seen INF1s. For those of you who don't know, INF1s are an inferential machine learning chip that resides on a C5A. Or no, C5. So it's a C5 under the hood, and it has an extra chipset on it. Who cares if you don't use it? They're really cheap on the spot market sometimes because nobody else uses them either, right? So AWS has a bunch of this excess capacity. They sit on the spot market. Nobody uses them. Having a tool that has a broad idea of what instance types are available out there and being able to leverage them can save you a ton of money. Whether you just use them in your lower environments because that's all you're willing to accept the risk in, or whether you use them all the way up through the stack. I would strongly recommend, again, this is where a strong DevOps team comes in. If you've got a strong DevOps team that can put your foot down and say, look, we're going to be 50% spot by end of Q3 this year. Mandate. You're going to do it or you're going to have downtime, period. Force people to do it. Once you do that, now you can save a ton of money because now you can switch out instance types. Similar instance, the R7 family in the fall. Huge amounts of memory. These are a 1:8 ratio box. There's a ton of memory on these boxes. They were super cheap. We were scheduling them and our customers would have terabytes of unused memory in their clusters, but the CPUs on them were so cheap and they were latest generation. Customers were getting better performance, better throughput, better application metrics because they were using these R7s and they were super cheap. So they were getting better throughput with less money because they were using the latest generation boxes that nobody else had picked up yet. Typically takes like 3 to 6 months for a new instance type to really start gaining traction in the market. In that 3 to 6 months, they're really, really cheap on the spot marketplace because they have a high capacity of them They launched them. There's a bunch of them in the regions, and nobody's using them yet because nobody has manually gone in and updated their node groups or manually gone in and recycled all their EC2 VMs or their GCE instances to use these new instance types. So they're just sitting around waiting for people to use them. Last year, I'll tell you one last story about this. The C3 family in GCP. We have a very large customer in GCP, one of the largest GKE users in the world. They run about 200,000 CPUs across their clusters. Probably the best DevOps team I have seen in my time here. Everything is on Spot. 99.95% of the workloads are on Spot. Sorry, go ahead. Was there a question? No? All right. Last year, when they launched the C3 instance family on GCP, they were 0.4 cents per CPU hour. Least expensive in the entire world. Out of all the cloud providers, they were the least expensive Spot instance anywhere. We automatically started rotating those into their cluster. By the end of month one, they had saved $250,000 on their clusters across the world. All of their clusters that ran across that 200,000 CPUs, they had saved $250,000 in that first month. That lasted for 6 months. They saved $1.5 million off their cloud infrastructure costs. Completely unexpected windfall, right? They were then able to go reinvest that into other purposes. They were able to reinvest it into more headcount. They were able to reinvest it into, being able to expand out into new regions. They reinvested that $1.5 million. At the end of 6 months, GCP increased the price of those Spot instances 4x. They went from 0.4 cents to 1.6 cents. We automatically ripped them out of the cluster and put something better in, something that was lower cost in, because the cost per performance wasn't that good anymore. But in the meantime, that customer saved $1.5 million without even trying. They literally didn't realize it was happening until they looked at their bill and they said, they noticed how much lower it had gotten. Absolutely amazing savings. So effective use of Spot instance and keeping your mind open to what instance families are out there and what you can use is very effective to be able to lower your cloud bills. And this is something I've been kind of working on. It's time to shift right. Everybody has been talking about shift left for the past 10, 15 years, putting things into code, infrastructure as code, security as code, testing as code, etc. There are some things that don't belong in code. Auto-scaling doesn't belong in code. Auto-scaling belongs at runtime, right? We don't statically define the number of nodes in code. We give it a range, right? 0 to 10, 3 to 20, whatever it is. Runtime is where these decisions should happen, right? You can control the policies and the higher level things in code, but we should be trusting automation to be making the right decisions at runtime. Workload sizing is another one. I didn't really touch on workload sizing too much today, but workload right sizing is always done in code today, right? People set their requests and limits in code. I get asked this all the time. Well, are you going to do a PR back into my code base with the new requests and limits that you recommend? No, not. Absolutely not. Why would we do that? Because they're going to be changing at runtime. You should be defining what you need for resources at runtime, whether it's your HPA, your horizontal scaling, whether it's your vertical scaling on your pods. Sure, put some guardrails around it and have those guardrails be what goes in code. But the actual auto scaling should be done with automation at runtime. That should be shifting right. We should be trusting the machines to make the right decisions at runtime. And that's how you end up with very efficient clusters. I'm going to break that right now. I want to show you a couple of examples. This is a 21,000 CPU cluster. It's currently at nighttime, so it's spinning down. They're at 94% requested to provisioned. The industry average on this number is 62%. They're 32% higher than average. This is where cost savings come in. They've reduced 32% of waste out of this cluster. You look down here at the graph, at night they're going down to 5,000, 6,000, 4,000, 5,000 CPUs. They're scaling up. 22,000 CPU in the middle of the day. I don't know if you guys can see it that well, but the dark blue line on top is how much they're paying for, and the light blue shaded area is how much they're asking for, how much they're requesting. They're very tightly matched. This is automation at play, right? This is the use case that we need. This is allowing runtime to decide how much capacity I need and trusting it to do the right thing and building resilient applications that are going to be able to auto scale up and down based on those needs. This one touches on requests versus usage. So the requested is a little bit lower here. Their used is higher than the 13%. This was actually 38% when I first brought this up a little while ago. They ebb and flow throughout the day. This is a perfect example of being able to auto scale effectively, using spot instances effectively. This cluster is, let's see, 477 spot instances out of 507 nodes. When we first started working with this company, they were 100% on demand. Over the past 2 years, they've migrated to 90-ish, 90-something% spot instances. They've moved to very high efficiency. Down here, you can see the used number. So they're using, during the daytime, they're using 7,400 CPUs out of their 22,000. That's not bad. I mean, it still seems like a low number, but this is incredibly good compared to most environments that we interact with. And lastly, they have 0 GPU workloads. They have 0 GPU requested, but we have 631 GPUs in this cluster. This is what I was making the point of earlier. This customer is using almost exclusively G6s right now. They're using a ton of G6s right now because they're very, very cheap spot instances and they're saving a ton of money. When they first came to us, they were using 16,000 CPU for $550,000 a month. Today, they're using 26,000 CPU. On average, it's 24 and change, almost 25,000 CPU. They're paying $250,000 a month. They're paying half 2 years later on a monthly basis than what they were 2 years ago for 60% more capacity because they're more effectively utilizing it. They're getting rid of the waste. Their used percentage is much higher. Their requested provision percentage is much higher. As a result, they're paying $250,000 for what's about $800,000 worth of infrastructure if they were using the traditional methods that they had used 2 years ago. This cluster would be close to $800,000 a month. Today it's $250,000 a month. This is success. This is what every DevOps team should be striving for, because this is what we actually got called out for saving a company from bankruptcy last year, right? The DevOps team got brought up on stage and celebrated. Has anybody in this audience ever heard of a DevOps team getting brought up on stage at a company all hands meeting and getting celebrated for saving the company from bankruptcy? I'd never heard it before. It was absolutely astonishing. They had saved so much money by optimizing their Kubernetes bill. I think it was about 70% cost of goods sold reduction that they were able to keep the company from going bankrupt. Absolutely amazing. Like, this is the impact that a properly tuned Kubernetes cluster can have. I think that's about all what I have left. Oh, and here's the result, right? Blue is provisioned, gold is requested. Here's what things look like with a properly tuned environment, right? This is what life should look like. This is what we want to shoot for. There's a little bit of waste in here. That's unavoidable. There's always edge cases, especially on large clusters, but you get it as tight as you can. The delta in money on this side to this side was about 40%. So if you're paying $100,000 a month for what's on the left here, you're paying around 60 for what's on the right. That's a lot of dollars. That's 2 jobs. It's 2 people's jobs every month. And when it comes down to it, I mean, that's right now we're going into a recession, right? Times are tough. We're hearing about layoffs all over the tech industry. That's 2 jobs we could be saving by doing a good job of tuning our infrastructure. Okay, I've been blabbing for what, almost an hour now. That's all I got. I think that's my last slide. Yep, that's it. Anybody have any questions?
All right. Question?
Question about auto scaling node groups and how much to trust. So we're on GKE. We've got a couple of spot node groups just in case, availability or whatever. Is there, and the HPA, you can say, right, schedule the cheapest node group. How trustworthy would you feel if you said, hey, here's 20 or 30 spot node groups, one kind of per instance type, and then let that node autoscaler choose the right group?
So it's not bad as long as you don't have taints and node selectors on all of them. As long as it's just going through the stack, as long as those node pools are available to a wide swath of workloads, that's an option, right? It's not a terrible option. The big issue with that mentality, and I've seen people use that before, if it goes deep enough that it has to fall back to an on-demand node group at some point, they'll stay on demand until you go in and manually move them off. That's kind of one gotcha there. But if you have enough depth of different, spot options, you'll find something eventually, usually, unless there's kind of some weird issue. So it's not a bad way to do it. I have seen people do that and get decent results with it. The big thing is making sure that all of those node pools, if you had the 20, make sure they're not all different node selectors or they're not all tainted, because if you got 250 different workloads, you want all 250 workloads to be able to land on any of those nodes, so that you're getting decent compression.
Great, thanks.
Yep.
So I have a question. So the requests of workloads is an input, to the size of a cluster, like the nodes that you provision. And so, like garbage in, garbage out. So like when you optimizing a cluster, like where do you see the most effectiveness? Is it on the like the node types that you use, in the cluster, or is it right sizing the workloads, individual workloads themselves? Or I mean, ideally probably a combination of the two, but like where do you see the most leverage?
Yeah, absolutely a combination of the two. Typically the DevOps teams that we work with have more control over the node selection and node choices. So they typically go that route as their first pass because it's less headache for them, right? There's less people that are going to get upset if they're shuffling nodes around, because most of the developers have no idea what's happening in the actual infrastructure. Changing requests and limits is a little scarier, because now if the workload does have an issue, the dev team is going to come and point their finger at the DevOps team. So from a real dollars perspective, the requests and limits are really a bigger savings because they're so egregiously over provisioned. But from a DevOps pain point, typically the node selection is easier to get a quick win, to get that 30 or 40% savings, and then they'll slowly work the request and limit fixing up through like staging and eventually in prod. But that tends to be a much slower process because everyone's afraid of breaking stuff and getting yelled at. Oh, and by the way, on request and limits, for anybody who isn't aware, set your request and limits equal on memory, please. Always. Memory is non-compressible. If you make a big argument of I need way more memory than I want to request, fix your architecture, fix your application, because you're gonna end up paying for it one way or another, either with kills or with bigger nodes that have more memory anyways, because you're just gonna be worried about kills in prod anyways. So just set your request and limits equal, and if it looks terrible, then fix the application. Right? There's ways to fix applications so that they don't do that. Mitch, you had a question?
Yeah, I was going to ask, so you said you'll have workloads move back to on-demand when there isn't spot capacity available, right?
Mm-hmm.
And so what does cast, does it do anything to try to move them back to spot instances?
We do. So yeah, I've kind of tried to keep this relatively agnostic, but I will address how we do it. With cast.ai, we don't use node groups or node pools at all. We spin up, for instance, in AWS, we'll spin up an EC2 instance of whatever the proper size is when we upscale, and we'll join it to the cluster. GCE, we spin up a GCE instance and we join it to the cluster. So we're not constrained by the same constraints that node pools have. So we don't need to set up the 20 or 30 different node pools to do that staggered kind of cascade fallback. As a result, it makes it a lot easier for us. So for us, if there's no spot capacity available in a shape or size that's going to be less expensive than on-demand, we'll automatically fall back to on-demand and schedule an on-demand instance, and we'll call it a fallback instance, right? We'll mark it as a different color. We'll call it fallback. Every n number of minutes, we'll automatically try to move that workload back to spot once there's capacity available again. So we'll try to spin up spot instances in the background. Once we get one that's more cost effective than the on-demand instance, we'll gracefully migrate the workloads back to that spot instance. So we can float back and forth between spot and on-demand. And this kind of goes back to my point about, about automation being key, right? It's incredibly hard to do that without writing a bunch of tooling yourself. There's a couple of open source tools out there that do something sort of similar, but it's all automation, right? You have to have automation that's able to do that because it's very, very hard to do by hand.
Yeah, I've got I waited to the end because this is only tangentially related, but assuming you've got your cost down, I'll give you a hypothetical that isn't so hypothetical, that we want to charge various business units that are running on the same, Kubernetes cluster kind of in a commune, but we want to give attribution, in charge, at least know how much each one of these business units is using.
Mhm.
Do you have any suggestions for that use case or?
Sure. So I'll show you our way of solving that problem. We have cost monitoring for workloads. So you can break down the workload costs on a per workload basis. So you can do this by either labels or namespaces or specific workloads. We actually have an option to do cross cluster. Actually, let me jump on a different one real quick. So this is my personal environment. So we have what's called allocation groups. And again, this is our personal platform. There's a few other tools out there. There's one open source one that does some similar stuff, but it doesn't do cross cluster, I don't think. So depending on kind of what your needs are, there's a few different tools out there. With allocation groups, you could do cross cluster on our platform. So you could select multiple clusters. I always use Datadog as a good example here. People lose track of how much Datadog costs them to actually run operationally. I've seen customers that were paying $5,000 or $6,000 a month to run the agents and the daemon sets for Datadog, which gets kind of lost in the whole licensing conversation when you're talking about, a Datadog or a New Relic or, Lacework or Wiz, any of those things. Being able to understand what the operational cost is across 50 or 100 clusters is really important. And also, to your point, being able to identify what your teams are actually charging and what your teams are actually costing is very important. So our tool does that. There's a few other tools out there on the market that do that, some open source, some paid, but it's very effective. And it's doing it the Kubernetes native way, using either namespaces or labels or whatever mechanism you want.
I was going to just follow up on the prior question about allocating, from spot to on demand.
Mhm.
And would you just if you have workloads that are more resilient, would you just taint them as spot only to prevent those from getting migrated, or would you use a different strategy?
So us personally, our fallback nodes that are on demand look exactly the same as spot instances. So the workloads can migrate between the spot workloads can migrate between them seamlessly. If you do have specific nodes that are on demand only for your on demand workloads that can't tolerate spot, I would taint those, because what'll end up happening is you'll fill up those nodes that are on demand with your spot capable workloads. And then the next time you need another on demand node, there won't be any space left, and it'll go create a new on-demand node that'll be partially filled, and then your spot workloads will fill up the rest of it again. So you'll end up with way more on-demand than you really need. So in that case, I would recommend tainting on-demand, and then or you probably might need to taint both, or just use node selectors. But if you're using a tool that can float between the two, then it takes that off your plate. You don't have to worry about it.
Yeah, I was asking specifically the reverse of right, I don't have time sensitive workloads that I want to wait for spot for, margin reasons.
Oh, yeah, absolutely. If you got batch jobs and you just want them to run on spot when there's spot available, sure. Just leave them on, on spot and say, just never go to on demand, only use spot when there's capacity. And yeah, absolutely.
So do you suggest to your customers that they use reserve instances in the case where they're using?
So I would actually move away from reserved instances altogether and just move to CSPs. Or in GCP's case, flexible CUDs, and I think Azure still has. I think Azure has flexible RIs or something like that. Just because that gives you the most options. I've actually seen people who had RIs on M4s, and they were 2.5 years into their contract, and they still had to run M4s because they had bought a huge chunk of RIs on M4s. M4s were antiquated way before that, right? They were already long in the tooth when they bought their RIs, but it was what they were already using. So as a result, they were getting garbage performance. They were actually more expensive. They were paying more for those M4s than if they had moved to a comparable M5 or M6 and just paid the flat out on-demand prices, because every generation gets cheaper. So I would desperately try to stay away from doing locked-in RIs on a specific family or a specific instance type, and instead just go with the general CSPs. And I would buy the bare minimum. We've actually had customers that had a CSP, they had a FinOps person. They went out and bought a CSP that covered 100% of their on-demand usage. They started optimizing and they were able to get about 40% reduction in their CPU count. Well, it didn't impact their bill whatsoever because they had CSPs that were covering all of it. So as a result, they got jammed up for, it was a year and a half or 2 years. They had signed a 3-year commit on a very high volume of CSPs, and they were stuck with it. Even though they were optimizing and didn't need it, they were screwed. So be very, very cautious about long commits. Staggered commits are much better. If you could do like a quarterly CSP buy, even if the first quarter you only do like 20, 25%, the next quarter you do a little bit more. That way they're always rolling off a quarter at a time. You're never going to get jammed up too bad. But the savings on a 3-year, if you're going to do a 3-year, only do it for a small percentage of what you need for on-demand, because technology changes, right? Your team might redesign the workload. It might be able to go on Spot a year from now. And if you've got a massive commitment on-demand, you're jammed up, you're screwed. So CSPs should be, they're kind of pitched as the silver bullet in the FinOps world, but they can be a very expensive, very damaging investment if you're not careful.
You also, on your spots, since the spots are specific to the capacity within the zone in AZ.
Yep.
Do you go across the AZs, meaning if you had what is it, G6 or whatever the ones you're saying in one AZ, would you flip over to another AZ if there are availabilities of those spots?
We do, absolutely. So like, let's see what we got here. So AZA has 153, AZB has 110, and let's see, AZC has 219. So AZC is probably the least expensive AZ available. So we will fill that one basically until we run out of capacity. If there are things like topology spreads, we'll still honor them, but we tend to steer towards the least expensive AZ, and that's where we buy capacity. If there's no capacity in that one, we'll go to whatever the next best option is. So in this case, we've got most in AZC, the next in AZA, and the last is AZB. So we do go wherever the capacity is and wherever it's cheapest.
Can you show me the instance availability map?
Oh, I haven't. Yeah, I should show you. So we do have this handy dandy little map. Once it loads. So you can actually see kind of which areas, which regions have the, let me see. So like US East 1 or US East 4, this is GCP, has a fairly high interrupt rate, but it's only in AZC right now. So AZB and AZA are better. US East 5 is not nearly as bad, Columbus, Ohio. So being able to, pick which regions, in this case, US East 1, GCP, US East 1, look at the interruption rates there. That's pretty awful, 15% interruption rate. And this is another point that I didn't make in the presentation. Picking less used zone or picking less used regions to spin up your clusters, internet performance is relatively the same across all the regions, right? It's very rare that you actually need to be close to something physically. Like all of these regions are going to have similar latency to the whole East Coast. So why would you go in US East 1, and even to a lesser extent US East 4, when US East 5 is going to be a better option? US East 4 is not a bad option. So picking the right region is really important, and it definitely has an impact on cost. It's way worse on Azure, or on AWS rather. US East 1, or where's US East 1 here? There's US East 1. Like US East 1 has a pretty high interruption rate, and let's look at the spot prices. Spot prices are the most expensive in US East 1. Whereas if you go to, where's US East 2? US East 2 is better, still not great, but better for sure. Same thing out west. Actually, US West 1 doesn't look that bad right now. Usually US West is worse. Sorry, go ahead.
Yeah, this tool, it covers all the cloud providers for the big three.
The big three. So we got AWS, GCP, and Azure. Azure is actually not too bad. Azure doesn't get interrupted that much.
You don't cover Oracle?
Not yet. We're actually probably going to add them this year, which is kind of funny because we all used to work at Oracle.
Yeah, I was gonna ask, how are you getting that data, the interruption rate? Like, are you just provisioning? Is that just based on a group that you provision and then you just track which ones get?
So these are all the clusters and instances that we manage. So we're tracking it across our whole data set that we have visibility into.
Oh, okay, gotcha.
Yeah.
Because I was gonna say if they have an API or something that I didn't know about that you could.
Oh, I wish. We've asked. So we have a really good relationship with all three cloud providers. Actually, 3 weeks ago I met with AWS and Azure up in Seattle, and then flew to Google Next and talked to Google at Google Next. So we've got a good relationship with all three of them, and we've asked that, and they're like, "No, we don't plan on doing that."
Not that good of a relationship.
Yeah, not that good of a relationship.
So speaking of the regions, I mean, it's not typical, depending upon the size or the compliance or actually the constraints, you would have multi-region. But in that case, like a DR scenario, you would manage across regions as well and that kind of a thing.
So typically what we've seen people do in the past for that is, set up a your load balancer, or even use like DNS load balancing to do multi-region, and have your primary and your secondary. Basically your secondary, you can scale all your workloads down to one replica, right? Because they're not taking any load. And then as soon as you flip that DNS load balancer, and maybe it's automatic. I did DNS in a past life. I used to work at Dyn DNS. Dyn DNS had health checks, right? So if one region went down, it could automatically steer traffic to the other region. There's going to be a slight warm-up time, but when you're talking a DR scenario, a 3-minute fully up to capacity warm-up time is effectively nothing compared to the old page somebody in and 20 minutes later you've actually done your DR failover. So the DR there is actually not bad. Using DNS load balancing and setting up your stack exactly the same in 2 regions isn't a terrible DR strategy, and it doesn't cost you that much if you're running everything at min replica.
And your tool would take in that consideration as well.
So what we would do, if you switch traffic from, say US East 1 to US East 2, as soon as that traffic hit US East 2 and all your HPAs started scaling up, a tool like cast.ai or one of the other tools out there that does similar things, we would provision all the capacity necessary for all of that horizontal scaling in parallel. So within about 45 to 50 seconds, you'd have all the capacity you needed for that first wave of scaling. There might be a second wave of scaling as the HPA continues to kind of catch up. But typically within like 2 to 3 minutes, you'd be fully back up to scale. So you take a 2 to 3 minute hit on reduced capacity compared to, 15, 20 minute downtime while you paged in somebody, and 15 to 20 minutes is being generous. I've done DRs before where, it was hours. Automation definitely helps there. It's not going to fully do it. You still need to have some good architecture in place, but automation is going to make a world of difference.
Well, one follow-up question. That would assume that these cloud providers will have enough capacity in a DR scenario, because if a region goes down, all of the customers from that region will then have to move over to that alternate region. And that's where the capacity issue will basically come in. So yes, I do understand where you have the mechanism to auto scale and all, but that is assuming that all that capacity will be available.
I'll be honest with you, almost zero digital native cloud native companies who are using cloud have an actual DR strategy. So if you set up US East 1 to US East 2 DR, you might be the only one. DR is not very well managed. DR strategy is usually we're just going to go deploy our Helm charts in a new region or run Terraform against a region. Very few people out there actually have a legit DR strategy. So as a result, I don't think you'd get nearly the inrush of new users in that region until probably a couple hours after an outage actually happened. If it was an outage that was lasting a couple of hours, right? If you lost all of US East 1 for 2 hours in any of the cloud providers, you'd see an inrush where everybody was scrambling to get stuff stood back up. But if you were able to react within 5 minutes and everybody else took 2 hours, you wouldn't have an issue. You'd already be stood back up before anybody else was getting capacity. yeah, DR in the cloud is kind of a dirty little secret that nobody likes to talk about. It's awful.
It is, but then there's some peoples that are not technical that somewhat demand it, right? So
Yep.
depending upon your industry or whatever, it's just part of the, you have to deal with, but,
Clouds are perfect and they never go down, so.
that's right. They never,
Network is infinite, clouds never crash.
yeah, how many nines?
How many nines do we need?
Yeah, I mentioned this earlier in the call. I used to work at Oracle. We lost an entire region for like 3 hours one time. Luckily, there was effectively no customers on that region, but it was a live active region. It just had very little usage. It was one of the far flung. It might have been Qatar or something like that, and it was down for like 3 hours. We had to literally use the cell modem to get back into it to reset stuff. It was that bad. So yeah, like, occasionally you can lose entire regions.
Any other questions? Well, let's give Phil another round of applause.